Okay, good morning, or evening, or whenever you're watching this. So last time we started talking about fluids, and one of the most important properties, or one important property of fluids, is how they are affected by temperature. So this brings us to section 12, which is entitled Temperature and Heat. So we have a good qualitative understanding of what temperature means. If you can touch something, you could say, oh, this is hot or this is cold or something like that. Heat we usually use very qualitatively, meaning we heat up something or cool something down. What we're going to do is try to understand these more quantitatively. So first of all, to measure the temperature of something, quantitatively, we want some property that's going to be affected by the temperature of the object, some property that we can measure. This is what we call a thermometric property. Thermometric meaning one that can be used to measure, that's what the metric means, the thermo or the heat in the object. So a property that we can use to measure the heat or measure the temperature of the object. Well, one very simple property that is very often used is the volume of something. When something heats up, typically it expands. So as the temperature of the object goes up, typically its volume goes up. When the temperature of the object goes down, often its volume goes down. Now volume is a very easy quantity to measure, so if we can make a correspondence between the temperature and the volume of the object, by measuring the volume, we can figure out what its temperature is. All right, well, there are several different temperature scales. So here we have a thermometer, and the thermometer works because it has some liquid inside, whether it's mercury or alcohol or something like that. As the liquid heats up, it expands, and the top rises up the inside column of the thermometer. By measuring the height of that column, we can then determine what the temperature is. So, one temperature scale is one that was developed by a scientist who studied heat by the name of Fahrenheit. His temperature scale, he defined in terms of two different temperatures. 0 degrees was the temperature of the coldest day in winter, and 100 degrees was his average body temperature, or what he thought was his average body temperature. From that temperature scale, he determined then that water froze around 32 degrees Fahrenheit, and water boiled at about 212 degrees Fahrenheit. Once those were determined, that's actually then how the Fahrenheit temperature scale was defined in terms of the freezing and boiling point of water. And then body temperature turned out to be not at 100 degrees, but about 98.6. So that's why average Fahrenheit body temperature is right around 100, because that's close to where Fahrenheit actually defined it. The metric, or the Celsius or centigrade temperature scale, is the one that we will typically be using, is then defined according to these same temperatures of the freezing point and the boiling point of water, but they are defined as 0 degrees centigrade and 100, excuse me, 100 degrees centigrade. So those are two different temperature scales. There will be a third called the Kelvin temperature scale, which we'll talk about later on. Okay, so we've got the centigrade temperature scale. 0 degrees is when water freezes, 100 degrees is when water boils, and then Fahrenheit, which typically we won't be actually using in class, but I mention it every now and then. Water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. We can determine a fairly easy corresponding equation between these two, in that the temperature in centigrade is equal to 5/9 times the temperature in Fahrenheit minus 32 degrees, while the temperature in Fahrenheit is equal to 9/5 times the temperature in centigrade plus 32 degrees. So we can go back and forth from one to the other. The Kelvin temperature scale actually has a 0 Kelvin as the absolute zero temperature. Now we will talk more later on about what temperature is actually measuring, but it's where the internal energy of an object is actually at its absolute lowest point, where there is no internal energy to the object other than just the energy of the atoms themselves. And so 0 Kelvin is what we call absolute zero. And that corresponds to negative 273 degrees centigrade. Now this number 273, that's something that we're going to see quite often, and so that's going to be a number you need to remember. 0 Kelvin is negative 273 degrees centigrade, or 0 degrees centigrade is equal to 273 Kelvin. So a change of 1 degree centigrade is the same as a change of 1 Kelvin. So the difference of those two temperatures are the same. One change of 1 Kelvin is the same as the change of 1 degree centigrade. In terms of Kelvin then, water freezes at 273 Kelvin, while water boils at 373 Kelvin. Okay? All right, now how do objects, either solids or liquids, respond when their temperature changes? One thing we said was that one thermometric property is volume, and that volume changes. Well, let's take a look at how solids are affected by temperature changes. So let's look at a little thing here. I have a metal ball, this is actually aluminum, and a metal ring, an aluminum ring. And let's notice that this ball just goes through the hole in the ring, so that they are really just the same size. There's not much wiggle room in there. Now what I'm going to do is heat this ball up. Heat this up, hopefully not heat me up. There we go. So I'm going to heat the ball up. And now, once it's heated, we notice it won't go through the hole anymore. It's too large to fit through the hole. However, if we cool it down, it goes right back through the hole again. So by heating up the ball, we actually cause it to expand, and it will expand enough that it actually wouldn't fit through the hole anymore. Now, why is this? What's going on? Well, we can understand this fairly easily. Imagine you had a crowd of people like this classroom, our class. If everyone were to stand up and stand very still, we could pack everyone fairly close together and make a fairly small volume of people, you might say. But now, if everyone started moving like this, the whole crowd would spread out. They would push each other apart, and the whole crowd would expand. Well, that's exactly what, well, maybe not exactly, but that's pretty much what's going on with the material. When we have atoms and molecules in a material, when they're cold, they have very little internal kinetic energy. And so they can get fairly close to each other. But as we heat it up, heating it up means adding energy to the object. And that means adding internal kinetic energy to those atoms and molecules, so they start moving around more. And as they move around, they start pushing each other further apart, and so the whole material expands. That's why things will typically expand when we heat them up. What makes volume a good thermometric property. Okay. So let's look at this quantitatively. So let's look at a one-dimensional object. So let's imagine we've got a rod or something like that. As that rod heats up, it's going to expand in all dimensions, but let's just look at one dimension of its expansion. So let's imagine we start out with a rod that is originally a length of L naught. We heat it up, and it expands an amount, we'll call it delta L. Let's see if we can figure out what sorts of things might affect this amount that it expands, delta L. Well, we might think that the original length might affect delta L. And actually that makes a lot of sense. Imagine we had two rods of exactly the same length. Each one would expand an amount delta L. Well, if these rods were actually connected to each other, each one expanding an amount delta L, well, if we started out with a rod then a length 2L naught, we would expect it to expand a length 2 delta L. So the amount that the rod expands depends on the length that we start with. The longer the original length, the longer it's going to expand, or the more it's going to expand. Likewise, we might think the more energy we put in, the greater the temperature change. The more these things move around, the more they'll push each other apart, the greater the expansion, and that is also correct. So the larger the temperature change, the more it's going to expand. And then we might guess that different materials would expand different amounts. Some might expand a little bit, some might expand more, and that's also correct. So we can put all of these ideas, these three ideas together, into a single equation to look at the linear expansion of an object. The change in its length, we said, is going to be affected by its initial length, or its unexpanded length. So we'll put L naught in there. We also believe it's going to be proportional to the temperature change. The greater the temperature change, the greater the expansion. So we will put in a delta T. And then we expect it to be affected by the different kind of material that it is. Copper might expand differently than, say, steel, for example. So we'll put in a term here which will be determined by the material. And alpha is what we call the coefficient of linear expansion. And different materials will have different values of alpha. Okay?